The last example I want to look at here is what I'm going to call a clever algebra example. So there are some integrals where you use integration by parts and it makes it look like you're going in circles, but we can do some clever algebra and end up getting a solution out of it. So this clever algebra example is where we take the integral of e to the x sine of x dx. And we don't know how to integrate that. We've got to pick a u and a v. Now, in this case, for problems that use this kind of clever algebra trick, it doesn't matter typically what you choose for u and v. So I'm just going to pick them at random, but you could have just as easily done it the reverse way. I'm going to say that u equals sine of x, and dv is equal to e to the x dx. This means that du will equal cosine of x dx, and v will equal e to the x. You can run through and double check those yourself, but yeah, just from practice, I know that that's what it's going to do. And I did it in my head here. So with all of that, we have our function integral, or our rule, integral of u dv is equal to uv minus the integral of v du. And that will be equal to, what is our u? It is sine of x. Actually, I'm going to write out the full expression here for a reason that will become apparent later. But for now, just bear with me. This implies that the integral of e to the x sine of x dx is equal to uv, so e to the x sine of x minus the integral of v du. So e to the x cosine of x dx. Now, looking at that, doesn't look like it helped. You know, this still looks pretty much exactly the same, but bear with me and let's do u substitution one more time. So u is equal to, in this case, our u is going to be cosine of x, which means our du is equal to negative sine of x dx, and our dv is going to be e to the x again, dx, which means our v is equal to e to the x. So now, what we have is, again, e to the x sine of x dx, our original expression, and then we used integration by parts to get e to the x sine of x minus, and now this is the bit that we're going to use integration by parts again on right here. So that's going to be uv of the new uv, so e to the x cosine of x minus the integral of v du. So what's v? It's e to the x, du is negative sine of x, so I'm going to put that right here. And, you know, we're back to not getting any simpler. It's still, you know, a mess or not helpful. But those of you that are kind of looking at this and kind of looking at patterns, you may have noticed something. Those of you who haven't, you know, I'll joke here and say, you know, prepare to have your mind blown with this. But let's start looking at this expression and start doing some algebra to start cleaning things up. So again, all that we've done is we've taken our original integral, then we rewrote it as this expression right here. Then we rewrote that whole thing as this expression right here. So all this is saying is everything on the left side equals everything on the right side. So I'm going to leave that left side, e to the x sine of x dx equals e to the x sine of x minus e to the x cosine of x. Now there's 1, 2, 3 negative signs, so that means this ends up being negative again. Integral of e to the x sine of x dx. Now if you look at this, you'll probably be thinking, if I point it out to you, well, Mr. McKinnell, this doesn't help us because this is just right back where we started. So why is that useful? And it's because it is right back where we started, except we've got this minus sign in here. So what can I do? I can move this to the other side, right? I'm just doing an algebraic manipulation, adding this whole chunk. And what does that mean? That means on the left-hand side, now I have two of these integrals, e to the x sine of x dx is equal to e to the x sine of x minus e to the x cosine of x. And now, hopefully most of you are starting to realize, like, wait, I wanted to find what this was equal to. So if I have twice what I want, all I have to do is divide everything by 2, and that will give me my answer. Just like that. So the clever algebra is if we think that this is going to run us in circles, that's good because it can run us in circles to the point that then we can move it and combine it and then just divide through by 2. And if that feels like I did something wrong or there's circular logic or something like that, take the derivative of this and see what you get. Assuming I did this right, we should get my original function. So let's do that right now. So the derivative of 1/2 e to the x will be 1/2 e to the x times sine of x minus cosine of x. So I'm pulling the 1/2 out front of everything. So that will get multiplied through at the end. Now I'm going to use the product rule. So I take the derivative of e to the x, which is e to the x, and then I write sine of x minus cosine of x, don't change it. Now I'm going to add now I'm going to add e to the x times the derivative of what's in this in these parentheses, which is going to be e to the x times the derivative of sine of x, which is cosine of x, and then derivative of cosine of x, which will be negative sine of x. So then, if we work on this e to the x can come out front, and I'll have 1/2 e to the x. And then I've got sine of x minus cosine of x plus cosine of x plus sine of x. And so the cosines will cancel, and I get 1/2 e to the x 2 sine of x, which is just equal to e to the x sine of x. So again, all that we did here was integration by parts multiple times. It ended up giving us something algebraic that we could rearrange and be clever about to actually solve for what we wanted.